Hello! Today we're going to continue our introduction to Newton's laws. Another law, Newton's second law. What is this law? Last lesson we familiarized ourselves with the results of Newton's first law and found out that a body can either be at rest or moving in a uniform and straight line, if there are no other forces acting on it or if they are compensated for. But then we might ask ourselves, what happens if the forces are not compensated? That is, their sum is not zero. What happens then? Naturally, it's logical to assume that the velocity of this body will not be constant. Even say that there is a certain acceleration. So if the velocity is changing, so there's an acceleration and the body starts to move unevenly. That's what Newton's second law is all about, which describes the motion of a body moving with acceleration. If in kinematics you and I just talked about a body moving with acceleration and described it in terms of the laws of motion, and talked about the acceleration itself as something that happened, then here we have to understand why this acceleration happened. So dynamics, as a branch of physics, differs from kinematics in that it studies the nature of how this motion comes about. Naturally, in this case, we will talk about different forces that lead to the acceleration of these bodies, but most importantly, we must understand how Newton's second law works. So what is this law? It's a formula that was derived by Newton as a result of his experimental research, so it was derived by experimental data, and it looks like this. That is, the acceleration that is gained with a body will be directly proportional to the force acting on that object, and inversely proportional to its mass. So we can do all sorts of experiments and find out really that if we apply a force to a body, and the body has mass m, and we apply a force of magnitude f, then in this case there will be some acceleration. In the figure we can show it like this. What happens if we double, for example, the mass, that is, we put another object on top of this object, in which case we realize that the mass would be twice as much. But by applying the same force, we get half as much acceleration. So it's the result of an inversely proportional relationship. So we can show it like this. Or vice versa. If you apply twice the force to the same mass, you get twice the acceleration. So depending on what happens in the problem, how the conditions change, we will see how the acceleration of this or that object behaves. Based on Newton's second law, we can get a decoding of the unit of measurement, Newton's unit of measure, that is the unit of force. If we want to calculate the force itself, it's equal to the product of the mass of the body and its acceleration. And so let's break down what 1 Newton is. 1 Newton. In this case, we're measuring mass in kilograms, acceleration in meters per second squared. That's the basic unit of force that we can write the Newton in. But as a rule of thumb, we don't need to do that in a problem, so we leave the unit of Newton. But sometimes, in order to get the final value, unit of some derived quantity, we need to know what it is. So we'll remember that and we'll use it if we need to. So, when we're talking about Newton's second law, it's our job is to keep a close eye on what forces are acting on this body and in what direction. And this is where understanding how the resultant force is calculated, acting on an object. So we can use Newton's second law when there is a single force acting on a body. And in this case, have already seen the application of it. But what if there are several forces acting on the body? In this case, we use a concept called the net force. The net force. In this case, it's the force that's acting on the body and replaces all the forces acting on that object. That is, we thus carry out a vector summation of all the forces acting on this object. There can be quite a lot of them, but the outcome of this course of action will be the same effect that one force creates, which will be equal to the sum of all these forces. And for Newton's second law, of course, we can use the same notation. which is to write the acceleration through the sum of all these forces acting on this object. This is what concerns the action of forces on one body. But what happens if several bodies connected to each other move under the action of the given forces? Let's say we have several objects that are connected to each other by some rope, and they're moving across some table, and we've applied one force acting on these objects, and it's pulling them in this direction. If there's no resistance from this table, this system will have an acceleration. And this acceleration will be the same for both bodies. Now, if you can see that in this problem, all the bodies that are moving with the same acceleration. Then we can apply Newton's second law to the system as a whole. So we can say that both bodies, that let's say it has a mass of m1, this body has a mass m2, they're moving with the same acceleration, which we define as the ratio of the total resultant force acting on this body, in this case the force F, and divided by the total mass of the whole system. In this case it is the sum of the masses of the given bodies. But that's only if we clearly understand that the acceleration of both bodies in this problem is the same, and it can be directed in different directions. So we'll be looking at these situations in practice. But the most important thing is that the acceleration is the same in modulo. Then Newton's second law in this format can also be applied. This application allows you to quickly solve problems when you've got multiple bodies moving with the same acceleration, and you can easily find the acceleration through Newton's second law. Another interesting case arises when there are forces acting on a body at some angle to each other. And that's when it makes sense to say that we can also look at the projections of these forces, their components, on the corresponding axes. Let's look at this. An example of this vector pattern. Let's say we have two axes, and the force acts on the body in this direction at some angle alpha to the x-axis. Then in this situation we can look at the components of this force as projections onto the corresponding axes. That is, we can break it down into two components. We get then component fx and fy. Then it turns out that the body acquires acceleration in two directions at the same time, i.e. x-axis acceleration and y-axis acceleration. In both of these directions, Newton's second law will work, which we simply write taking into account the given projections. For example, for the x-axis projection, we write the equation like this. For the y-axis projection, we'll write it down in this format. And then our job would be to calculate the projections of these forces on the corresponding axes and get the acceleration along each direction. This will help us to work with problems where the force starts to act at certain angles to the direction of motion of the body. And will help us realize that in different situations, the acceleration can work along one direction of motion, along another direction of motion it may not. You and I talked about this back when we studied kinematics and considered the motion of a body thrown at an angle to the horizon, where the motion was in two planes and the acceleration only worked along one of them. This is a clear case where a given acceleration is produced by a particular force, which is directed to the same direction as the acceleration, and it doesn't change direction as it goes along. Well, I'll say goodbye for today, and I'll see you in the next lessons. Goodbye.